Nobel laureates in physics and chemistry, laureates in economic sciences, members of the Academy, ladies and gentlemen. The role of science is to question what is regarded as the truth, to uncover hidden phenomena, to see the possibilities which are obscure to the ordinary mind. The passionate observer, equipped with imagination and creativity, leads us forward to a world with better conditions. We stand on the shoulders of giants. As science develops, new giants appear and show us the way forward. Some of them are with us today. The progress of mankind is very much connected to materials, the way natural materials can be exploited and used, and how new man-made materials can be developed. Materials have even given the names to the ages of civilization, the Stone Age, Bronze, Iron, Silicon ages. Man is not able to do anything without materials. It is essential to understand the properties and uncover the hidden secrets of materials and unexpected states of matter, and to be able to design entirely new and intelligent structures constructed using the smallest possible building blocks. Today's intelligent man-made materials would have been pure science fiction just 50 years ago. It is not possible to plan for the unknown. New fundamental discoveries that may lead to applications which could not be foreseen, and the period between a fundamental discovery and eventual applications is often very long compared to the criteria commonly used by governments and funding agencies. But with the words taken from Vannevar Bush, the American engineer and science administrator, as long as scientists are free to pursue the truth, wherever it may lead, there will be a flow of new scientific knowledge to those who can apply it to practical problems. During the last century, we have witnessed an explosive growth of science and technology, a development nobody could even dream of at the beginning of the last century. The French advocate of enlightenment, Jean-Antoine de Condorcet, he argued that the expanding knowledge in the natural sciences would lead to progressive development of human capabilities and lead to a world of individual freedom and moral compassion, since, as he believed, social evils are the result of ignorance and error rather than an inevitable consequence of the human nature. In this respect, he seemed to be too optimistic when it comes to how humans treat each other. We still see corruption, dishonesty, and unethical conduct in otherwise well-developed societies. However, new theoretical tools for properly designed and formalized negotiations help us to deal with conflicting interests. Today, science and scientific knowledge are needed more than ever. We live in a time with widespread resistance to knowledge, where even powerful world leaders deny scientific knowledge. A new term, post-truth, has been added to the Oxford Dictionary, meaning how emotions affect people more than facts. We need to trust in science, because only knowledge can make the world better. Alfred Nobel, he recognized the importance of science and those who uncover what has been hidden, who explain our mere existence, who improve the quality of our lives, who open doors for future findings. This week is the big celebration of science. And today, you are all welcome here to listen to some of those who have increased our knowledge and made a difference to the way we think. I will now ask Professor Thouless Hansson, member of the Nobel Committee for Physics, to introduce the Nobel Prize in Physics.
So, good morning, everybody. So I'm very happy for this opportunity to say a few words about the Nobel Prize in Physics 2016 and introduce the laureates who are going to give 2016 Nobel lectures in physics. So here they are. I'm sure that many of you already know their names. It's David Thouless from University of Washington, Seattle, USA. It's Duncan Haldane, Princeton University, also USA, and it's Michael Kosterlitz, Brown University, United States. So the citation of the Academy that motivates the prize is for theoretical discoveries of topological phase transitions and topological phases of matter. And I will not make any attempt to explain what that means to you. You will hear 2 lectures later that will try to explain to you what that means. Okay. So I will instead say just a few words about the laureates. So I start with Professor David Thouless. He was born in the UK, 1934. He got his PhD from Cornell University in the United States, and he's now the emeritus professor at the University of Washington, Seattle. And I should tell you that Professor Thouless is a legendary person among condensed matter physicists. So he has made really groundbreaking contributions to theoretical physics. I will not take time from the lecture to list all his achievements. But I should mention that although he's awarded this year's Nobel Prize for his work on topological states of matter and topological phase transitions, many physicists might hold the view that his work on mesoscopic physics, where he introduced the very central concept of Thouless energy, might be as important as the work that we are celebrating today. His achievement has earned him many prestigious awards, including the Maxwell Medal and Prize, the Wolf Prize for Physics, the IOP Dirac Medal, and the Large Onsager Prize. Now, I already mentioned that I already read the citation, and as you can see, it has 2 pieces to it: topological phases of matter and topological phase transitions. These 2 subjects are intellectually closely connected, but they are still distinct, and they are going to be presented in 2 lectures by the 2 other laureates. And the first one will be given by Professor Haldane, and I will now say a few words about him. So he was born in London in 1951, got his PhD from Cambridge University, but ended up as the Eugene Higgins Professor of Physics at Princeton University, where he is now presently and still very, very active. And he has worked in many areas of theoretical physics. Again, I won't give any long list, but just mention that in addition to the work that we are honoring today, he has introduced important concept in physics, the concept of eluting a liquid, the concept of fractional exclusion statistics, and the concept of entanglement spectrum. And he has given seminal contributions to the theory of the quantum Hall effect. So now it's my pleasure to, I should say also that he's been awarded the Maxwell Medal and Prize, Oliver Buckley Condensed Matter Prize, the ICTP Dirac Medal. And now I will call on Professor Haldane to come up and give the first of the 2016 Nobel Lectures in Physics. Please, Professor Haldane.
Thank you. This is a rather challenging lecture for me to give because usually I give these talks to specialists, but I'm going to make an effort to give you some flavor of three kind of surprising discoveries that both David Thouless, who I'm going to talk for a bit, and myself have made. And these are all things which I think were not expected at all at the beginning of whatever calculations were done to reach these things, and they all emerged as surprises. And I heard from Marcel Denys about this, David's work on this thing, and it's again a similar thing that they didn't realize what good stuff was going to happen until almost the end of the calculation. Okay, so I thought I'd give a little bit of background for what I'm going to do, because I'm not sure who I'm talking to. But of course, you just recall high school chemistry. You've got orbitals that get filled. I've probably gone one back before. Yeah, sorry. You have a set of energy levels in atoms that quantum mechanics makes discrete, and you can get to fill them up with electrons. And in the usual case, you can put 2 electrons in each orbital because they have something called spin, which goes up and down. And I'm going to make an analogy for this because this is actually what's going to happen in the quantum Hall effect. And the simple case of the integer quantum Hall effect, we have a 2-dimensional surface on which electrons can move with a large magnetic field going normal to the surface. And in a magnetic field, electrons go around in little circles, just like in the atom. But now it's the magnetic force that drives you in a circle, a force at right angles to the motion of the electron. And in this case, as the radius of the orbit gets bigger, that corresponds to larger kinetic energy of the electrons. So in that case, we have, again, an energy level diagram where we can fill up the orbitals. But instead of having, as in chemistry, a 1s orbital, a 2s, and a 2p, and then 2d, we actually have a large number of orbitals. And in the quantum Hall effect, the integer quantum Hall effect, the number of orbitals is macroscopic. It's proportional to the area of the system, the area in which the electrons are able to move. And there is one independent orbital for every quantum of magnetic flux that passes through the area, the system. So that, in case you haven't seen any of this stuff before. So if I have a fixed density of electrons, let's choose, because the number of orbitals in each of these levels, degenerate levels, is proportional to the magnetic flux density, the magnetic field. We could choose the magnetic field just right so we can completely fill up the lowest set of orbitals here, the lowest Landau level. We call these degenerate set of orbitals Landau levels. And if I take this system where I just tune things just right, so there's exactly the right number of orbitals to be completely filled by the electrons in the lowest Landau level and the others are all empty, we get something that appears initially to describe the integer quantum Hall state that turns out to be the earliest of the topological states of matter that were experimentally found, and that was found by Klaus von Klitzing in 1981, and very quickly, because of the implications, it led to his Nobel Prize in 85. So when you have this situation, you've got an energy gap. If you're a chemist, you'd call it the HOMO-LUMO gap or something. And so this is a kind of rigid system that you filled it just up to this level. It's going to cost you energy to put any electrons in a higher level. And so if I try to squeeze the system, where I'm actually changing the area in which the electrons are allowed to move, and therefore changing the number of orbitals, if I compress this thing down, I will not be able to compress it any further than having filled this Landau level up completely, because I'd have to, if I pushed it together more, I'd have to put things in the next Landau level, which costs me a lot more energy. So at first sight, it looks that's a very fine-tuned thing that you'd have to get everything just right. And the special feature of the Hall effect that von Klitzing found is it's very robust. But actually, this is a topological system, and because something has to happen at the edge, you don't actually need to fine-tune anything to get this just right. Because at the edge of the system, if I think about the electrons going around in little, do I have a light here? I can't see it. Yeah. If they go around in little circles, I've drawn them going around in clockwise circles here. But if they actually reach the edge of the system and try to go around in a clockwise circle, they go bang, and they will bounce back off the wall. So in the orbits that hit the wall will actually precess around the wall in the anti-clockwise direction. And that's one of the hallmarks of topological systems. They have strange states at the edge of the system. And this is what we call the edge states. They're counter-propagating edge states that have this remarkable feature that they only allow propagation around the edge in a single direction. And of course, that's because if they can only go one way, it means if I looked at the thing backwards in time, they'd be going the other way. And this is a system with what we call broken time reversal invariance. The magnetic field breaks the symmetry of systems under the change of direction of time. So the orbitals at the edge actually go up a little bit, and therefore there's a reservoir of electrons at the edge. The Fermi level is the highest occupied state, the chemical potential, and as I change the magnetic field, I will be changing how much I fill this thing up at the edge, but I will still maintain the gap in the bulk of the system. So this system does have gapless excitations at the edge. There's a gap which is very small. It's proportional to the length of the 1 over the length of the edge, so it's a microscopic gap at the edge of the system, but I still have in the interior this large bulk gap, which is a topologically protected state. Well, what von Klitzing found, he did these measurements of, he measured the Hall resistance, the Hall resistivity, but I'm going to talk about the Hall conductance, which is 1 over that. So what he sees in the picture, you change the magnetic field, and the Hall conductance sticks at various values, which turn out to be quantized, and it turns out to be an integer times these fundamental constants e squared over h, or e squared over 2 pi h bar. And being an integer is what finally got understood to be a topological property. Topology, we heard from Hans Hansen at when the prizes were announced about you counting the number of holes in bagels and things, and those can't be other than integers. These are topological properties that we'll see. And this is actually what a very nice result of David's has been. Okay. So the von Klitzing system is much dirtier than the theoretical toy model I presented to you. It's got all kinds of details of junk inside it. And the work at the early 80s focused on these difficult problems of how you treat disorder and randomness and what was going on. But the work I'm going to tell you about of David's is he had the idea to study not the effect of this kind of random dirty system, which is difficult, but just a simple periodic system, add a kind of crystalline background of his choosing to these Landau levels. And Marcel Denys, who worked on this, said at the end of the day that was David's brilliance in the thing that he actually chose a tractable problem as opposed to sticking around the physically relevant problem was apparently the disordered one. And we have this sort of situation. The ideal case where it's clean in the middle is perfectly flat. And this is a case where Bob Laughlin, who won the prize a little bit later for the fractional quantum Hall effect, had earlier given an extremely powerful argument that says if I have this flat system in the bulk and the only places where there's energy levels at the Fermi level or at the edges, then if you apply this electric field to make things flow, the charge would flow across the system in a way that couldn't be affected by any kind of dirt because it was too far for any scattering between points at one Fermi energy and the other Fermi energy. And so here there was a very clear argument that related a gap in the bulk region of the sample to this perfect quantization of the Hall conductance, where it's just given by a whole number times fundamental constants. So the actual problem that people trying to be practical or trying to be realistic would have tried to solve is this one here, where there's a lot of junk in the middle and a dirty potential. But as I said, this is very difficult, and what David took some very beautiful results from Hofstadter and solved this problem here, which should be a perfectly periodic wave in the middle. The potential is periodic, which means some points the lowest state in the system will be down here, and the highest state will be at this point. So the lambda level, which in this case is a perfectly flat, infinitesimally thin energy level, gets smeared out into a range of energies between the top and bottom of this periodic potential. And that's this so-called TKNN paper, the Thouless, Komoto, Nightingale, and Denies. I guess some people trying to be cute put TKNN squared like that, but the other three were three postdoctoral collaborators. Komoto was David's postdoc, and Nightingale and Denies were other people's postdoc, I guess, at University of Washington, Seattle. Anyway, they together with David, they looked at this problem of what the presence of this simple periodic potential added to the Landau levels would do to the integer quantum Hall effect. And the bottom line is they discovered a remarkable formula that they hadn't been looking for, and that, according to Marcel Denies, it jumped out of them only at the very end of the calculation. Okay. They were too concerned with the details, but at the end they suddenly saw something was important. So David had been particularly interested in this very interesting toy model a lot of people were kind of fascinated with at the time. It often goes by the name of the Hofstadter butterfly, because you had an extremely beautiful pattern come out, and Douglas Hofstadter found this in the 1970s, and he loved his aesthetic appeal, I guess. It's a model of a crystal in a magnetic field, and people have gone to town on this model because it's got all kinds of beautiful features in it. But basically, it's just the same model as before: kinetic energy of particles in a magnetic field, and then of just the simplest possible periodic potential, a cosine potential in the x direction and a cosine potential in the y direction added together. And this thing's called the butterfly. It's usually shown rotated sideways, and I guess it's got tremendous amount of fine structure and fractal structures floating around in it, but that's not what's interesting us here today. It has these very narrow levels, which I guess for the purposes of calculating the Hall conductivity, this is done by Yossi Avron and his former student. They donated this picture to me, so there's no copyright concerns in my lectures. And so the numbers here tell you what this integer should be. Here at the bottom, this thing is not the Landau levels, but it's very close to the Landau levels structure. It's almost identical to what you would see for a simple Landau level structure. And you've got a lot of very narrow levels, and when you fill the first one, you get one filled level, the second one two. But when you look in this other structure, you get all kinds of other weird numbers floating around. And they got fascinated, the team got fascinated and saying, first of all, how can you calculate these numbers, these integers? What are they? And so the basic point that Marcel tells me that David pointed out was that Loftin's argument tells you if you've got a gap in the bulk of the system, you've got to get this integer quantization coming out. And Loftin had done it for the simple Landau level case, but this thing also has gaps in the bulk, and if the chemical potential's in there, you should get quantization. And they were struggling to find out what was the formula that get these integers. Okay. And so after they solved lots of equations and found the thing, they realized they found how to calculate these integers. They found there had to be a more general principle than just solving what were called Diophantine equations, the mathematical structures. And basically, if you take you've got a periodic potential, it's actually not the usual kind in a crystal, because there's the periodic. The unit cell you have to use is not the simple one of the cosine potential. It's related to how many of the unit cells contain an integer number of magnetic flux quanta. So it's a rather strange band structure. But basically, if you've got something periodic, there's a Bloch theorem that says you can write the wave function of a eigenstate of a system in a periodic potential as two things, a periodic function times an exponential e to the I k dot x or k dot r. And the details of what's going on in the bands are all contained in this periodic thing. So they took a very standard formula, a fundamental formula for the calculating the conductivity of a system called the Kubo formula, and plugged this stuff in. So the Kubo formula is usually used for calculating the dissipative part of the resistance. But in the case where you're looking at this whole resistance, where you're looking at the response to an electric field which is parallel, which is at right angles to the motion of the current, so it doesn't dissipate any energy, you get different formulas. Well, they put this in and they cranked the handle, and they eventually got a very nice formula. They didn't actually comment on it in the paper, that how nice this was in some sense, but they ended up with a formula that depended only on the details of the band structure, which are of the wave functions of the band structure, which are contained in this function here. There's no reference anymore to the energy levels of the problem. The energy levels are there in the Kubo formula, but after integrating stuff out and using formulas for the velocity of the system, you find the energy levels when you're calculating this whole conductance, this one which is dissipative, not the usual ohmic law conductance, the energy levels all drop out. So this was the first form they got of a formula. And after I'll show you in a minute how this turns into an integer, but they found this formula which gave you the Hall conductance, which is these numbers e squared over h, which is von Klitzing's number of 25,310 ohms, I guess. Ohms to the minus 1, sorry. And then we have these numbers here, which you can do some simple mathematics with Stokes' theorem on. So they found this formula. And shortly after they published their paper, another very influential discovery in physics was that Michael Berry discovered that the adiabatic approach to quantum mechanics had missed out an important geometrical phase, and in fact this is another piece of work that a lot of people think should get the Nobel Prize. This is my hint to the committee. But it's geometric, so I guess you can say it shouldn't have come this year. Anyway, that's my... So Berry's example was a spin which was polarized along some axis, and you gradually rotate this, and you find that you pick up this additional phase, which is very geometrical. It's actually the solid angle, the spin times e to the I times spin times the solid angle enclosed by the path, which is ambiguous modulo 4 pi, and therefore the spin has to be an integer or a half integer, which we knew for other reasons. But these are typical of these topological things that have interesting consequences. This tells you that spin has to be quantized, for example, even if you didn't do it by algebra. So anyway, the mathematical physicist Barry Simon, in 1983, just after the two papers had been published, I guess he recounts that someone else tipped him off about this connection, and he should look at it, there had to be a connection. And he found that the two things matched together very well, that the Thouless, the TKNN expression was an integral over a curvature associated with this phase of Berry's. It's a holonomy. And mathematically, it was an integral over a compact manifold, which turned out to be the Brillouin zone, which is topologically equal to a torus. And in fact, he pointed out this connection to what is really a mathematical extension of Gauss's famous Theorema Egregium, which I guess he discovered while he was a foreign member of the Royal Swedish Academy of Sciences, because he was joined in 1821, and this is 28. And he thought, I think Gauss seems to have thought this was the most amazing discovery he ever made in mathematics. So what Gauss discovered was what we heard from Thor Hans Hansen about the bagels and the thing. So Gauss discovered something that you can easily get the simplest version of it from your high school algebra class, right? So you know that the surface area of a sphere is 4 pi r squared, where r is a radius. And the Gaussian curvature that Gauss introduced, of course, for the sphere is uniform, and it's 1 over r squared. So if I integrate the Gaussian curvature over the surface area of the sphere, I get 4 pi. But what Gauss discovered as this amazing theorem was that I can change the shape of the sphere to anything else, like a football or a banana or whatever, and they still got 4 pi. And this is called the Gauss-Bonnet theorem, I guess because Gauss never wrote it up properly and Bonnet put all the details in later. So if I take this thing, we get this by now famous account of the Swedish and the German pretzels, and we also get the account that the famous relation between coffee cups and bagels. You have a mug is the same as a ball. What's being called a loving cup is the same as a Swedish pretzel, and I'm not quite sure what kind of loving cup this is because it's got 3 handles, but that's the same as a German pretzel. That doesn't I thought, well, I'm not sure if that's in the right nationality kind of combination, but anyway. So this is the topology that you see every year when people give talks about topological insulators. They love the coffee cup. I'd like to see actually the Swedish pretzel changing into the loving cup and backwards, rather it be a change from the coffee cup and the bagel. So, okay, the formula that they found, that Barry Simon pointed out that this formula was really the first Chern class integral. Well, basically, it can divide it into 2 parts. It's 2 things. It's the integral of a curvature, which you can write as an antisymmetric tensor, but now in momentum space, not in real space, or K space, block space. And then this is the formula. The other part of the formula is the formula for the Berry curvature. And in fact, it's kind of interesting fact that, again, talking about things which are discovered before their time, this formula is in a very correct paper, or something like this formula, a 3D version which is non-topological, is in a 1954 paper by Karplus and Luttinger that was denounced as completely wrong and nonsense for many, many years. Only in 1999 was it recognized that it was actually a case of Berry curvature, and somewhat later it was shown to be essentially correct in a lot of situations it's been applied to. So this, again, topology formulas are not obvious until so I guess Barry Simon did a very big contribution in pointing out the mathematical framework of what David and the other collaborators had found. So just quickly, in these formulas, if we write them down, people make a big correspondence now to think of things like something like electromagnetic fields in momentum space, because the curvature is kind of like the magnetic field, and the curvature can be written as something like the curl of a vector potential, which is called the Berry connection. And the Berry phase is the integral of the Berry connection around the closed path. And it's very much like the Bohr-Maharonov phase when you take an electron around a loop and in the presence of a magnetic field and try to calculate what phase it picks up when it goes around that loop. And the Berry phase, because the Berry phase is e to the I something, this is a number which is only defined modulo 2 pi. From this, you quite quickly see the mathematics of Stokes theorems tells you that the integral of the curvature over something bounded by a curve has to be 2 pi times an integer. So this was the form that Thouless found. The actual form they wrote in their paper looked something like this. They'd integrated by parts the first formula, and then they found this thing has to be, when you do the mathematics, is obviously an integer times e squared over h. And that was the thing. So, in fact, as I said, Marcel Denys told me that this only emerged at the very end of the calculation of kind of afterthought. He has some talk about they realized there was an elephant in the room after looking at their formula. There had to be something a lot more in their paper than just the actual values of these numbers in this nice colorful diagram, right? The numbers, of course, were not interesting, really. I mean, the only challenge is that you can compute them, but then the big picture, rather than being interested in Hofstadter's butterfly, the big picture is to come out with a very fundamental formula that no one had expected existed before. And this is this amazing work that he did. Okay, so this is right. So out of this, my own work, which was also mentioned a bit later, comes from seeing that this integer quantum Hall effect can actually occur without Landau levels. So maybe you could say this was implicit in the TKNN result, but I don't know, it wasn't noticed. The 1982 paper was all about the periodic potential on Landau levels, and it hadn't really been appreciated that if it's a topological thing, the details surely can't matter, and the specific realization in terms of Landau levels is very complicated and not very practical for hopefully finding new materials, right? And so I was, again, stumbled over this feature that you could actually write down a very simple model. It turned out to be very influential because you can do very simple calculations with it. It turned out to be something like graphene. It's a modified form of graphene where you have second neighbor electrons can tunnel between second neighbors and they pick up a little bit of a complex phase, which is a time reversal breaking effect as they hop around. So you end up with an extremely simple kind of so-called tight binding band structure. And it turns out to really be the first of the topological insulators. This is a time reversal broken topological insulator, which in my view actually has more potential, practical potential than the normal kind that people are studying a lot now. But we'll see what happens with this. So this has actually, it's kind of graphene. At the time we didn't know that someone would invent graphene by taking a Scotch tape and on pencil, scraping a pencil over something and doing Scotch tape. So I put in my paper that this would be a single monolayer of graphite, but it would be inconceivable for someone to actually realize that. And of course, I think the lesson is that material science can take us to play. If it can be done, someone will do it, right? However crazy as long as it's not real black holes and something like that, whatever the crazy model you come up with, if it's just something interesting, it's most likely someone will be able to make something that does it, whether it's cold atoms or the other ways. So one of the features of these systems is that they have this one-way channel around the boundary where things move in one direction. In the Landau level case, that was really coming from the direction of the magnetic field. But in graphene, if you look at it, graphene, you call an edge of graphene. There's various edges, and there's a nice one called the zigzag edge mode. And you find that graphene has itself at the edge. If I take a view along the edge, there's actually a bound state which comes between two different Dirac points in graphene and exists in part of the surface Brillouin zone. And it connects these things. Once you can open up a gap in graphene by turning it from a semi-metal to a semiconductor in two ways, by breaking inversion symmetry or breaking time reversal symmetry. When you break inversion symmetry, you get something boring. This state has to be attached to either the top or the bottom band. In the boring case, both ends of the state are attached either to the valence band or the conduction band. But in the interesting case, one point ends up attached to the conduction band, the other to the valence band, and there's a kind of channel, a plumbing connection between the two that you can drive states up and down by putting a magnetic field through this flake of graphene-like substance. And if I fill the system up to the Fermi level that's in the gap, I find I have these one-way, things that travel one way. This is actually the hallmark of the topological states. They typically have something very interesting at the boundary. And the start of all, about 10 years ago or 12 years ago, Eugene and Amelie and Charlie Kane did something which I'd actually thought of doing, and I never did the calculation. I thought it obviously won't work. They took two copies of my model and put them on top of each other, one with upspin electrons going one way and the downspin electrons going around the edge the other way, and I'd have thought that these things would mix and scatter, but there was a new topological invariant, which was something like -1 to the Chern number, that hadn't been appreciated before. So this was an extra topological invariant, not the one that Barry Simon had pointed out was what the TKNN formula was, and that has led suddenly to generalizations to 3 dimensions and people discovering lots of very interesting topological materials lying in laboratory shells. Okay, so there was this toy model, which is somehow a relation to the TKNN story, again has a very fruitful history. It's also been translated into photonics, and there's a field now of topological photonics where you get light to travel one way around the boundary of things. Okay, so the third thing, if I have time, I'll talk about. How much time do I have? 10, okay, is the magnetic chains, which also is about the same time, about probably within a few months of the quantum Hall measurements by Klitzing. All at this time, things are coming out, and this was actually been baptized by Xiaogan Wen, who's recently made a very exhaustive classification using very fancy mathematics of cobordism or cohomology or something to classify all possible subsets of topological things. And this, in some sense, is the hydrogen atom of topological materials, it turns out. Okay. Of course, I did not know that at the time when I found it. But it was something totally unexpected. And of course, that's the hallmark of topological materials. They differ fundamentally by some number being 1 or 2 as opposed to 0, which gives them a property that's not present in normal matter, and this stuff behaves very differently from what was expected to happen. Okay. So actually, this was an interesting case. I actually was unable to publish it at the time because these two journals dismissed this out of hand based on referees saying, it's in manifest contradiction to fundamental principles of physics, a bit like what happened to Karplus and Luttinger that I mentioned. And by the time it was published, there was actually a more sophisticated argument that actually removed what I realized had been the connection to the earlier work that we're going to hear next from Kosterlitz, the Kosterlitz-Thouless transition, because there's a very nice mapping from two-dimensional classical systems at finite temperature, where there's a Boltzmann factor describing a probability weight, to quantum mechanics in one space and one time dimension, where the Boltzmann factor gets replaced by an amplitude. And the quantum mechanics is richer than classical mechanics because Boltzmann factors are always positive, while in this case there may be some time reversal invariance, but the amplitude can either be positive or negative, and you get interference effects between one path having a positive amplitude and the other half a negative amplitude, and therefore the two things can actually cancel some process completely. So the thing was, in this paper, I see that, so this, my lost preprint, because I didn't have any records of it, it was just cited in people's work at the time, but Jieno Sholyum I found had finally kept a copy of it, and in fact it's kind of interesting to read it again, and it's actually basically using the Kosterlitz-Thouless argument translated to quantum mechanics to say why the conventional wisdom at the time was incorrect. Okay, you can find it on the archive if you want now. I posted it. So in magnetic chains, we have ferromagnets where they like to line up, or antiferromagnets where the opposite case. And this work dealt with a antiferromagnet in one dimension. Okay. And the feature there is, what was known at the time, is that the ferromagnet's got a conserved angular momentum, conserves its total spin, so it's kind of stable ground state. But the antiferromagnet, the quantum fluctuations in one dimension destroy long-range order. So people knew that as a mathematical theorem, but they had a remarkable thing. There was a exact solution of this magnetic problem for spin 1/2 system by Hans Bethe, who incidentally was David's thesis advisor at Cornell. And before he went off to tell us how the sun produces energy, he was interested in quantum chains. And he did a remarkable piece of work whose significance I'm sure he didn't understand, because he lucked onto a solution of this model that seemed to work, and it took about 50 years to discover why it worked. And Bethe clearly didn't understand why, because his paper says, my next paper will do it in 2 dimensions and 3 dimensions, but of course that never happened because this is a very specifically one-dimensional thing. But this was a very obscure, a difficult piece of work, and no one knew how to calculate anything else except energy levels from it. But in the mid-1970s, another piece of work, a remarkable piece of work, going back to the 30s, a Jordan-Wigner transformation, which maps spins, which are bosons really, to fermions by relating spin up to be filled and spin down to be empty states, gave a way to translate these spin chain languages into fermion language. And this actually was a lot easier to do calculations with than the beta ansatz, and it allowed one to translate things into calculations you could do. And I guess progress always happens when you can actually turn something to some calculation you can actually do on on a piece of paper or understand. Then you can understand all the details. And this was done by Luther and Peschel. Luther was at Nordita for a long time after that. And they turned this thing into a fermion problem, and to cut a long story short, they got most of it right, but they missed out some detail, which I discovered later by applying this Luttinger liquid theory that was mentioned. And I found that that they didn't really have an understanding of what happened when you went from an easy axis to an easy plane to easy axis antiferromagnet, where the spins were in the plane or wanting to point out of the plane. And looking at the numerical, this new tool gave us a thing to extract numbers from the beta ansatz calculation. They showed immediately some term was missing. And these pictures here are actually exactly the quantum translation of the Kosterlitz-Thouless story that Michael will tell you about. So it turned out that the spin half system was special rather than the spin one system. They both were Kosterlitz-Thouless transitions, were driving you from easy plane to easy axis, but there was a special cancellation effect, which I guess we'll vaguely say here, between in the spin half case. Here that you've translated what Mike's going to tell you about from a two-dimensional space to a space-time diagram, and here there's a tunneling process that takes you between a configuration where these are compass needles in the plane. They kind of stay in the plane, and as you go around this periodic boundary conditions, you go around. In the first case, there's no kind of winding number. The second case, there's a twist that's gone in, like a Mobius strip or something. A twist went in, and you can't get from those two things continuously. You have to do some kind of breakdown, and there's a tunneling point, which is a vortex. And it turned out that for the spin half case, you only got a double vortex, because if you have to do this process of tunneling on one of the bonds between the spins, and if you look at the process on two neighboring bonds, everything should be identical if the bonds were identical strength, except the two paths. In one path, one of the spins rotated 180 degrees clockwise, and the other one it rotated 180 degrees anti-clockwise, so the difference of the paths is rotating a single spin 360 degrees, but if it's a half-integer spin, you get a -1 factor. So the quantum mechanics told you something. So looking at this way gave you a completely new way to look at things, and it turned out that the conventional wisdom was completely wrong. And finally, so we came up with this new story which shocked people at the time, because it conflicted with preconceived notions based on the beta ansatz equation seemed to confirm incorrect ideas about spin waves. And finally, let's not go through this too much, but at the end of the day, this turned out, this new state with this gapped integer spin liquid state that I found turned out to be one of the simplest topological states with a very non-trivial entanglement. The spin one system, and the interesting thing is the spin one can be viewed as two spin halves glued together. And in the usual case, they just point in some direction, but here the spin one again splits, fractionalizes into two spin halves, which one on either side, and they grab onto the spin one half from the partner and the next one along, and get entangled into a singlet state. And when you do that, you get left the two spins at the end of the chain. They get left with one arm stretched out here and the other arm stretched out here. So there's like two half spins at the end. This is two unexpected spin one halves at the end of the thing, and this is precisely the analog of the edge states in the quantum Hall state. Again, this feature you find in all the topological states, that there's something strange happening at the boundary where the edges are, where things go from something to normal. So anyway, so that brings me to basically the end of the story. I couldn't really give you all the technical details, and it's probably quite confusing because it's very difficult to explain this to a general audience, even a general audience of scientists if they're not condensed matter physicists. But basically, my interpretation of why this prize was awarded now is because so much has suddenly, in the last 10 years, has come out of all this old stuff. These various little findings, which in each turn came from people finding something more amazing than they were looking for, just something, noticed something strange, and it gave you a new way of looking at things. And what's happened is that over my lifetime in condensed matter physics, I've seen that the kind of things we were taught and learned from textbooks like Ashcroft and Mermin and things back in the 70s, a lot of the details that were thought to be really important then are really, we put them away as boring stuff which doesn't relate, not important, and all kinds of new things like entanglement and new ideas which were not present in any of this old stuff have become the central kind of questions that we're struggling with. And this after the topological materials started to be found concretely as real things, there was also proposals that they could be used as a so-called platform for topological quantum information processing, and that, of course, has stimulated a large amount of interest. And there's been a huge amount of people in cold atoms, quantum information, condensed matter, even the string theorist Ed Witten is now devoting part of his time. I guess string theory is, there's some spare time out to deal with other things now, and they're getting very interested in extending all this topology to 4 dimensions. So we now have tables of topological matter up to 8 dimensions. So you can see how the influence from outside the field has influenced things. But this is a very exciting area because we're finding all kinds of what I consider neat stuff about quantum mechanics that we didn't know before, and there seems to be plenty of new insights to gain. So that when you can find something very simple and beautiful, we all think that's the truth, and maybe we're going to learn a lot about matter and learn a lot about possibly applications of it. Thank you.
There aren't any questions.
Sorry?
No questions.
Okay, so I'll walk out with you.
Yes. So thank you very much for this very inspiring, and I guess to many of you also challenging lecture. And now I will present the next speaker, which is the third of the laureates. It's Michael Kosterlitz. He was born 1943 in Aberdeen, United Kingdom, and he graduated with his PhD from Oxford University in '69, and he is presently the Harrison Farnsworth Professor of Physics at Brown University in the United States. And I know that he has Nordic connections. He visits Sweden, and he has also a close connection to Physics Institute in Finland. So Professor Kosterlitz have given many crucial contributions to the theory of phase transitions. I should mention in particular the Kosterlitz renormalization group equations that have been very influential in many areas of physics, not only the phase transitions in two-dimensional materials that we will hear about, but also, as was alluded to in the lecture by Professor Haldane, that there is a very deep and intriguing connection between classical physics in 2 dimensions and quantum mechanics in 1 dimension. And the Kosterlitz renormalization group equations and the Kosterlitz-Thouless phase transition has been instrumental for understanding also quantum properties of matter. Professor Kosterlitz has been awarded the Lars Onsager Prize and the Maxwell Medal, and he will now give the second 2016 Nobel Lecture in Physics with the title Topological Defects and Phase Transitions. Please, Professor Kosterlitz.
Thank you very much. Oops. Okay. Good morning. It feels a bit strange to be standing here addressing this august audience, because I never thought that I would ever end up in this position. But here I am, so I will do my best to try to explain how I got to this point, or at least tell you some of the story how I got here, and in particular pay homage to the man who really started me off in this field, David Thouless. Now, okay, let's see if I can get my computer to work. Okay, so the early work of David, which was very influential to our thinking in this field, he did in a very short physical review paper back in 1969. And it was incredibly short, just 2 sides of a piece of paper, if I remember rightly. And it was basically related to a simple model. It was just a one-dimensional magnetic Ising magnet with a Hamiltonian written up there in the first line, and it depended on, with different ranges, interaction ranges. Okay, so it was known that if the interaction range was longer than 1 over the square of the distance between spins, that there was no magnetization at any temperature and no phase transition. However, if the interaction range was longer, it was also known that there was a transition at finite temperature. It was a transition to a state of finite magnetization. David was asked, he visited Bell Labs, and he was asked, did he know anything about this intermediate situation of where the interaction range was exactly 1 over the distance squared between spins, because this was a strange situation, and nobody really understood what was going on there. And so, according to the story I hear, is that on the way back on the train from Bell Labs to Stony Brook, he had an inspiration. And typical of David's inspiration, actually rather simple, but extremely deep. And now this is the fascinating thing about David Thouless, that his ideas sound quite simple, but when you sort of think about the consequences, or the implications of what he says, you realize, wow, this guy really is deep. He's a very, very deep thinker. So you should never mistake the simplicity of the ideas with the depth, because it's often very simple ideas which are the deepest. Now, so what David simply said was very simple. Let's think about the system and imagine that it's at low temperature, so it's magnetized. And let's assume some magnetization. We're talking about a ferromagnet, so it's simple, no anti-ferromagnets, no difficulties. And, oh, by the way, I should mention that I am talking in purely classical, about purely classical systems. And the reason for this is that at the time when I got interested in condensed matter, I knew essentially nothing about the subject, and to me, quantum mechanics was just an unnecessary complication which only half understood anyway. So everything I'm going to talk about from now on is purely classical. So to come back to the problem, David said, all right, let's imagine having the system, a magnetized system. Now let's simply imagine flipping a segment of this chain of spins, just reversing the spins. Instead of call the possible values of the spins +1 or -1, and every time you see a +1 spin in this block, change it to -1 and vice versa. So if you do this, the energy change is given by this little formula at the bottom of the slide. So Now, the consequence of this is just that in this special case of one of our distance squared interactions, is that the change in energy is given by a very simple formula. It's basically twice the square root of the magnetization, mu is the magnetization here, times the exchange constant, times the logarithm of the size of the block you've decided to flip. Fine. So then you ask yourself, so what? What is the consequence of this? Well, as you probably know, we're in statistical mechanics, which is what we're trying to do here. The essential quantity that's of interest is the so-called free energy, which is just energy minus temperature times the entropy. And the entropy is nothing other than the logarithm of the number of possibilities. And the number of possibilities is simply related to the number of positions, of allowed positions of the reversal. And the number of allowed positions is basically n, the length of the block. So the change in the free energy is just energy minus temperature times the log times the entropy, and entropy is sort of Boltzmann's constant, this k sub b, which you have to put in to get the dimensions right. And so you get this little formula written down there. Now, the consequence of this is if there is long-range order, in other words, if it's magnetized, then we must have the coefficient of the logarithm of the size of the block must be positive. In other words, we're talking about low temperatures, so the first term must be larger than the second term in the bracket. And then we expect that assuming that does undergo a phase transition, so that some critical temperature called T sub C, that the magnetization disappears. And what has to happen is this free energy difference, this delta F, has to go to 0. Therefore, the critical temperature must be given by the vanishing of the coefficient of the logarithm of the system size. So we've got a formula that twice 2 mu squared J must be equal to KTC at the critical temperature. And remember, the magnetization, mu is the magnetization. Okay, now, that formula, which looks sort of very trivial, very obvious, has a remarkable implications. It means the magnetization must go discontinuously to 0 at the critical temperature, assuming, of course, the critical temperature is positive. So, now there was a lot of knowledge and lore about phase transitions available at the time, and what the sort of lore was saying that at a continuous phase transition, the magnetization should disappear smoothly as you approach the critical temperature from below. Okay? Now, assuming this is a continuous transition, this is saying, wait a minute, this formula is saying, wait a minute. No, that can't happen because the magnetization has got to jump discontinuously to 0 as you pass through the critical temperature. This is actually a very strange result, but because normally one thinks of a phase transition where something jumps discontinuously to 0 is what is called a first-order transition. But this transition is well known not to be first order. So this is a most unusual situation. Again, that's very typical of David. He comes up with these apparently very simple arguments which have the most extraordinary consequences. Trouble is that there's no way to argue that this argument is incorrect. So he's now found something unusual again. because he's found a very, very strange situation where we have a system where we have a so-called continuous transition, but it has a discontinuous magnetization at the critical temperature. So this is just the sort of argument which David Thouless produced, which has some extraordinary, at the time, consequences. It's certainly a correct argument, but what's more important from my point of view was in the work that David and I did together later, and I did myself, this argument, or this observation, was actually extremely influential. Now, so let me now tell you a very short story about how I ended up at Birmingham University. I was actually brought up as a high-energy physicist, and so I was really keen on doing the glamorous high-energy physics stuff. And I happened to be at a postdoc in Italy at Torino University with the ambition of going on to the standard place for high-energy physics afterwards, CERN at Geneva. But, as is my standard downfall, I failed to get my paperwork in on time. So I could not get a spot at CERN, and ended up sort of jobless. So I quickly sent my wife, or my girlfriend at the time, down to the railway station in Torino to buy an English newspaper where I could look for some job adverts and apply for whatever job I could find. So I wrote out a few applications, sent them in, and then got offered a job as a long-term postdoc at Birmingham University, which was, to tell the truth, the last place I wanted to go to, because I was determined to go to CERN in Geneva, but it wasn't to happen. So I ended up in Birmingham, and I did some long, tedious calculations, high-energy physics, for about a year. And I got really, really tired of it because, first of all, I didn't get anywhere. Second, just when I was about to write stuff up, or had written the preprint, I was starting to write up the preprint, then suddenly a paper would arrive at my desk doing exactly what I was doing. And so this happened 2 or 3 times. And it was these calculators were produced by some group in Berkeley. So after the second or third time with this, I realized it wasn't going to work, because here I was on my own, calculating away, doing things, and every time I almost was finished, the preprint arrived at my desk. So I was clearly not in a very strong position here. So in desperation, I went round the department in Birmingham asking, begging people for, if they had a problem that might be tractable, perhaps I could look at it. So eventually I ended up in David Thouless' office. And I listened to him talking about introducing to all sorts of weird and wonderful new concepts, things like vortices in superfluid helium films, and phase transitions in 2 dimensions. Of course, much of this was a mystery to me, because I actually had skipped statistical mechanics in graduate school because it didn't seem to be relevant to my proposed field of high-energy physics, which was a mistake. And also, as I say, I was in a place which was the last place I wanted to go to, listening to David explaining lots of weird and wonderful ideas to me, which I could barely understand. However, what David was saying sort of made a lot of intuitive sense to me. So I thought, well, maybe this statistical mechanics stuff, it could be quite interesting. So we started looking at some of these two-dimensional systems. And the situation in the early 70s is basically summarized on this slide here. And the class is a class of models which are basically cover all of the classical statistical models, and they're described by a Hamiltonian given up at the top of the slide there, where we considering a ferromagnetic model in 2 dimensions now, not 3, where we have got n spins of n components, and we keep the spin length fixed at 1, say. And so what was known about these models at the time? Well, not much was solved. The only solved model was the n equals 1 case spin up or down, otherwise known as the two-dimensional Ising model. Now, this was solved by most extraordinary calculation by Lars Onsager back in, when was it? In the 1940s. And in this model, yes, there is a phase transition, because we know that from the exact solution. The next case is 2-component spins. Now, this was interesting for physical reasons, because this would describe a model. It's a model for a thin film of superfluid helium-4. And what was known about this model at the time was, well, maybe there's a transition there. It might be, but who knows? If the number of spin components is greater than 2, then the simulations, high-temperature series expansions, etc., said probably there isn't a phase transition at any finite temperature. And the only thing that was really properly known is the limit of the infinite number of spin components, otherwise known as the spherical model, and an exact solution says this one in 2 dimensions has got no transitions. So clearly this situation needed a bit of further study, particularly because of the importance of the 2-component model, which could be a description of superfluid helium films. Now, there was a piece of experimental evidence floating around, and I show this picture here. It was in a Fizerev letter 1972, and this piece of evidence, this piece of experimental evidence tells us basically unambiguously that the n equals 2 case does have a phase transition, because you see, this is an experiment done by Marvin Chester and co-workers, and it consisted of looking at the resonant frequency of a vibrating crystal, and they absorbed some helium onto the surface of the crystal and measured the change in the resonant frequency. Now, as you all should know, the resonant frequency of some vibrating object is inversely proportional to the mass. Because the mass increases, the resonant frequency decreases. That's all you need to know at this stage. And so they did a set of experiments. And the dots are the experimental results. The straight line is what you expect, assuming that all the adsorbed helium sticks to the surface, because the film is so thin that any atom of helium that gets absorbed on the surface of the crystal, assuming that it's a normal, forms a normal fluid like water or something, that would, as the crystal moves backwards and forwards, the adsorbed molecules also move backwards and forwards, and therefore will increase the mass of the oscillating object. And so one would expect that as you put more and more fluid on, and the horizontal axis here is just it's basically a formula which tells you, where it gives you an exact measure of the total mass adsorbed onto the surface of the crystal. And so the initial data, when the first few molecules go in, follows the expected straight line. You can see that. But then, at some point, as you adsorb more and more helium onto this crystal, something very strange happens. Suddenly, there's a whole mass of adsorbed helium suddenly doesn't contribute to the resonant frequency. And so one can argue that the deviation of the difference between the experimental points and the straight line is a measure of the amount of superfluid, amount of fluid that has decoupled from the crystal. And so once it's decoupled from the crystal, what do? You wave your hands and call it a superfluid, because it is completely unexpected. Okay, so this piece of experimental evidence was staring us in the face, saying that, look, in this system, XY system, a planar rotor spin system, in 2 dimensions, there must be a phase transition. Now, suddenly, it does have a transition, which contradicts the standard interpretation at the time of some rigorous theorems which said that there is no long-range order in such 2-dimensional systems. And of course, this rigorous theorem, for many years, no arguing with the rigorous theorems, absolutely correct. But the interpretation could be argued with, because the interpretation of this theorem would say there's no phase transition because of the standard Landau interpretation that a phase transition implies that suddenly in the ordered phase you have long-range order. So here is a situation where there's clearly a phase transition, but there's a rigorous theorem that also says, okay, there's no long-range order. So the problem that we were then faced with is to somehow reconcile these two apparently contradictory statements. Clearly, the experiment says, look, there is a phase transition. There's the data. It's obvious. There's a phase transition. Okay, that's experimental side. The theoretical side said there's no long-range order. There's no arguing with the theorem, but so the only conclusion one can come to is that the theorem is correct, but it's not relevant. So it's certainly a phase transition. Now, this is typical David Thouless problem. He could see that there was a contradiction here that can be, should be looked at. My own take on the matter at the time was, I don't understand this. So what? Because I didn't know about these rigorous theorems and so on, but it looked like an interesting problem to work on. So I thought, okay, why not? So we started looking at it. Now, this slide, sorry it looks so busy, but I thought that I would redraw this thing to make it less busy, but of course the Nobel Week is so every moment of every day is scheduled for the laureates that there was no time to do anything. So I apologize for this overly busy slide. Now, so what do we know about? What's the situation? The first thing is we're talking about superfluid helium, or if you like, a spin model, where two-component spin model, where let's say assume that the length of the spin is fixed, so the spin configuration can be defined by this angle theta. And if you like, the superfluid order parameter is just the S sub x plus I times S sub y, which can be written in the form amplitude times e to the I theta, where theta is a phase. Now this whole system is invariant under the phase shifted by any multiple of 2 pi. So therefore we can say that the global excitations of this system, or the so-called topological excitations, are what are called vortices. And this is just a spin configuration where if you walk around a contour, some closed contour, then the change in the phase as you go around this closed contour is a multiple of 2 pi. And of course, it has to be a multiple of 2 pi because the order parameter itself has to be the same when you come, if you start somewhere, go around and come back, the system had better be the same thing that you started with. And so this order parameter, which I write as amplitude times e to the I theta, that has to be single valued. And so, therefore, the change of phase as you go round the contour, come back to where you started, must be a multiple of 2 pi, because that leaves the order parameter itself invariant. However, if the change of phase as you go round some contour is 1 or 2 or -1 or -2, what that's saying is there must be a singularity in the order parameter. Write it somewhere inside this contour. And of course, this sounds a little bit unphysical, because after all, what we're talking about here is a film of helium absorbed on some nice continuous surface. So how on earth can something be discontinuous? How on earth can we have a change of, a phase change of 2 pi when we just walk around a circle? Well, it's very simple. We say that, okay, we have got a vortex. What we've done is we've walked around a vortex. Say we've gone round, say clockwise, and we're changing the phase by 2 pi when we walk around some point in the middle, and then we can say the point in the middle, the blue blob in the middle, is the core of the vortex. And so what happens at the vortex core is, let's say, the magnitude of the order parameter, or just as either, it's just 0. So in other words, if you like, it's a hole. It's like topologically, it's like a hole in the surface. So of course, one can have a contour running around a hole where the phase change can be 2 pi. There's nothing wrong with that. Now, see if I can go back. Okay, now let's go back a little bit and ask, what are the consequences of this? Well, suppose we just make the argument, let's consider a large system, and let's consider an isolated vortex. Just put an isolated vortex in the system. And let's calculate the energy. Okay, the system size is It's an L by L system. The energy of an isolated vortex in this system is just proportional to the logarithm of the system size. It's log L over A, where A is some microscopic cutoff, like a lattice spacing or the vortex core size, something like that. The entropy change, or the entropy associated with this vortex, is simply Boltzmann's constant, to get dimensions right, times the logarithm of the number of possible positions of the vortex core. And, of course, the number of possible positions is just the total area of the system divided by the area of a vortex core, because that's the number of possible places you can put the vortex. And so you then get that the free energy is E minus the temperature times the entropy. So again, you get this logarithm, the logarithmic formula, a little bit like what we have in the one-dimensional 1 over r squared Ising model. And so you can then just say, okay, the central quantity in statistical mechanics is the free energy. So the associated free energy is just E minus temperature and entropy. So there's your two formulas for the energy and the entropy. So you just plug that in. And then you can say the probability of such a configuration, or if you like, of having a vortex, is, this is statistical mechanics again, so I assume you have to know something about statistical mechanics, and it's just proportional to the exponential of minus, sorry, I've written beta. By beta I mean 1 over Boltzmann's constant times temperature, e to the minus beta f, and you have a formula for the free energy. And so the probability of a vortex is the system size divided by the microscopic cutoff, like the core diameter or something like that, to the power of minus pi k minus 2, where k is just the exchange constant divided by Boltzmann's constant times temperature. So in other words, k is a temperature-dependent quantity which is large at low temperatures and small at high temperatures. And so this little formula here, that the probability of having a vortex, an isolated vortex in the system, is L over A, where so L over A is a huge number, to the power of pi k minus 2, where k is a quantity that is inverse in the temperature. So in other words, this probability of a vortex being present is 0 if pi k is greater than 2, as long as the exponent, the power is negative. That means at low temperatures, the probability of having a vortex is 0. And at higher temperatures, this probability, when pi k is less than 2, this probability has to be 1. Okay, of course, I've forgotten about other normalization of that formula and so on, but let's forget about these little details here. So in other words, this system should have a transition around the temperature such that this factor, this k, which is temperature measure, is a measure of the temperature, is larger than 2 over pi. Now, that is the essential argument of our original paper, which was published way back when in 1972, 73. And we can say that when this temperature-dependent coupling constant K is large, the topological sector, in other words, the number of vortices, because the probability of thermally creating a vortex is 0 at high temperatures, then you can say this single topological sector, the number of vortices won't change because there's a huge energy barrier to get over. It has to be stable. Whereas when the temperature is high, or alternatively this temperature-dependent parameter k is small, then there can be transitions between different topological sectors. And of course, what this in turn means is that, in principle, at low temperatures, you should have a superfluid, but at high temperatures, you won't. Simply because, so let's see why that should happen. Okay, now, let's think about a superfluid. For a moment, what is a superfluid? Let's suppose that the superfluid lives between those two vertical bluish lines. I'm sorry, these slides are not that good. It's because I had to make them all myself, and I'm not the greatest artist. I have to use whatever is available in the little program, so this is the best I could do. Now, in a superfluid, this is a system line between those two vertical lines. Let's suppose we've got a system where we've got a uniform flow in a downward direction with at velocity u sub s. That's the superfluid velocity. How can this decay? Because if this flow cannot be dissipated, then we have a superfluid. If it can be dissipated, it's a normal fluid. And the only possible way of doing this, of dissipating the superfluid flow, is to create a vortex-anti-vortex pair and see if they just simply drift further and further apart. And if they can get infinitely far apart, if you like, they go to the system edges and disappear poof. And in this process, they will unwind the phase and reduce the superfluid velocity slightly. So this is the central question. Now, if you're at high temperatures, these vortices can be produced, appear spontaneously and in large numbers. So this process will easily occur because this superfluid flow would simply cause the vortices to disappear to the sides, and the superfluid velocity would go to zero. All right, so what does this mean? This means that the fluid is normal. Because remember, equilibrium statistical mechanics is always talking about, if you like, the infinite time limit. So it doesn't care what happens at short times. Short times being is any mathematical time less than infinity. It doesn't matter if things take longer than the age of the universe to happen, but in equilibrium statistical mechanics, doesn't really care about timescales. So at high temperatures, because of the possibility of creating these vortices, clearly the any superfluid flow has to be dissipated by this mechanism I just talked about. At low temperatures, on the other hand, the probability of getting an isolated free vortex which can drift under the influence of a uniform superfluid velocity, they don't exist, and therefore you have to call that a superfluid. This flow will be at least metastable. So at least now we've got a mechanism for distinguishing between a superfluid and a normal fluid. And so therefore, the next thing we had to study was a system of vortices, which is, you may say to yourself, all right, I could, of course, give you the formula for the energy of some complexion of vortices and say we do the statistical mechanics of this. But that formula is so disgustingly complicated, and it's probably longer than I could write down in this PowerPoint slide, so I won't even attempt to do it. But it can be done. However, now David and I cooked up a theory which involved, remember, now here we've got a set of point vortices which interact logarithmically. Now, for those of you who have actually done electrodynamics in arbitrary dimensions, you'll immediately recognize this logarithm as a Coulomb interaction between charges. So one could regard the vortices as a set of point charges interacting with the Coulomb interaction. And so then, of course, once you've got this, you immediately think, dielectric functions, etc., etc., etc. And so one could think of the system in terms of an electrostatic theory. And this is basically what David and I did, or at least rather, let's say, well, David and I did back in 1972-73. And that paper is probably the most cited paper either of us have ever written. And it is basically correct, but in our calculations, we unfortunately made an incorrect and unfortunately unnecessary simplification, which messed everything up. And that calculation has since been straightened out, what, in 1979 or so, by Peter Young, who basically redid our calculation in a correct manner and pointed out the error that we had made. But also, I was bothered about the results of our calculation because the results didn't look right. I mean, just had a bad feeling about them. So I thought, okay, maybe I should try to do a proper calculation here and use this thing which was just appearing called the renormalization group. Of course, I actually learnt the renormalization group from a paper which David had kindly given me by Phil Anderson, Gideon Yuval, and Don Hamann, where they talked about the 1/r R² Ising model in the context of the Kondo problem, which was all the rage those days. And I spent about 6 months doing nothing but reading and rereading this paper. So we've got 0 minutes left. Okay, so eventually we got some results. So here are the results of my renormalization group calculation. Now, what this calculation says is that it actually makes some predictions. And what it makes a prediction of is the superfluid density at just below Tc as a function of the critical temperature. And what is interesting about this little curve, this little diagram, is that the theoretical curve is that straight line, which is the theoretical prediction. The various dots are experiments. And according to John Reppy, apparently the dots were all plotted without knowledge of the theory. And then when they learned about the theory, they put the straight line in, and to their great astonishment, it went basically right through the experimental dots. And so one could regard this as an excellent confirmation of the theory. So, and this is basically the reason why our theory has become quite well known, because it actually works and has been measured and verified in many systems. Not, of course, by me. I wish I had done it, but so I better stop there and thank, in particular, the Nobel Committee for awarding us the prize, and my wife and children for putting up with me. Thank you.
So thank you very, very much for this inspiring lecture, and in particular, I hope that all graduate students in the audience listened, so they might think a little bit what is interesting and not interesting, and what is useful and what is not useful in your further studies. And now I will ask all the 3 laureates to come up on the scene, please. Just keep it. And see you.